Thank you everyone for coming. It continues to be a pleasure to be back in rooms talking to people. It's very nice. For those of you who don't know me, I am M.Andrews. I work for Nokia Labs in New Jersey, but I work with a number of characters in the room. And this is my second visit to Links, so it's a great setup that you have here. So thank you for the invitation. So the genesis of this talk was that I told people I was going to be here, and Francois suggested that I give a talk. And really, the main thing I could talk about is a presentation I've been giving in a couple of places recently, which is really trying to give an overview of some of the work that we're doing on networking and robotics. And I think it's fair to say that a lot of this work is in reasonably early stages. And also, I think there's a lot of problems that remain. So I think you should view this as sort of explaining some of the problems that we think are interesting without necessarily, there's going to be no great theory presented here or anything like that. But I think there is some nice theory that could be done for a lot of the problems. So the title is Talking to Robots and Drones. So it's really about what are the network requirements for autonomous agents in factories and warehouses of the future. I'll motivate this as I go through the first few slides. Okay, so to a first approximation, I think you can say that there are two sorts of wireless networks that we all use. So one is outdoor wireless. 4G is the past, 5G is the present, 6G is the future, and it's outdoor cell towers talking to a device like this. And how would you characterize these? Well, I'll characterize them in three ways. So first of all, you've got high coverage. Pretty much wherever you go, you expect your phone to be able to work. Very careful configuration. So the network is very carefully configured to make sure you've got coverage and high capacity everywhere, and very sophisticated resource allocation. So generally, these are highly engineered networks that work very reliably. And then you have indoor wireless. So most of us will have Wi-Fi in our homes. Certainly in my home, there's various places Wi-Fi doesn't work. It's an ad hoc configuration. Typically, you go in and you put the access point down. And okay, there's resource allocation between devices in Wi-Fi, but it's not as sophisticated as in cellular. So it's generally a much more primitive but cheaper and easy to deploy network. But what's happening now indoors is increasingly we need to provide good wireless coverage for industrial deployments. So to give a motivation for this is a video from a Nokia factory in Chennai, India. And there's various devices that are going around here that are being talked to by wireless networks. So here is an AGV, a guided vehicle that's running on a magnetic strip, and then we have autonomous robots that are going to be driving around the factory. So as if we run the video, we can see that happening. So we see that there's this big guided vehicle going around transporting devices. We have this autonomous robot going around, and you can see there's another one. You can see there's a lot of people around, and you don't want these devices to hit things. You don't want them to hit each other. You don't want them to hit people. So therefore, there's a kind of a control problem here. You need to talk to the network. These devices need to talk to the network pretty reliably, because if the robot stops talking to the network, it either just stops and doesn't do anything, or it can start doing its own thing, which can cause a problem. You don't want to be driving it into people. So increasingly, and apologies for the people here from Nokia, because I know a lot of you know this story, but these slides were generally prepared for outside people. So there's a big push within, I guess, the industry to start thinking about wireless networks in these industrial environments. And one thing you could ask is, do you even need wireless networks in these type of environments? And for a lot of the equipment, maybe not entirely. I mean, robot arms could be connected wirelessly. General manufacturing equipment, cameras you could deploy with wireless, but with wireline connections. But still, people are looking at wireless because actually it can eliminate safety hazards. You don't need to put so many wires in, and also it's actually much easier to deploy access points than to deploy a lot of wires everywhere. But of course, the other thing is increasingly these environments will have mobile devices, and for those, wireless is essential. You can't have a wire running around after a robot. Well, in fact, you can actually. We've seen some companies that are having robots running around trailed by wires, but it's not. It's a fairly ugly solution. So what a lot of I'm going to talk about today is what sort of network do you require to talk to a robot on the ground and also a robot that flies in the air, aka a drone. So therefore, just going back to the earlier slides, if you have an industrial indoor wireless network, well, what are the requirements? Well, it's now an indoor environment, but now you actually do require reliable coverage. Wherever the robot wants to go, you want to have good coverage. You need reliable throughput and latency. So if you want to talk to the robot, you need good. You need to know what network conditions. You need dependable network conditions, and you've also got a lot of devices. So maybe you want to start having smarter resource allocation than Wi-Fi gives you among these multiple devices. So don't really want to give the company plug, but this is just the one slide saying how Nokia as a company is starting to address this. Is we have a product that's really a cellular network that you can deploy in a building, and they're going after as a market. They're going after airports, mining, ports, utilities, but in particular for manufacturing warehouse operations, manufacturing and warehousing facilities, they're seen as an opportunity for actually deploying a cellular type network, which gives you all the throughput and the latency performance that you get in a cellular network, but have it in these private environments. So in some sense, a lot of what we want to do, therefore, is figure out, okay, what do we need with these type of networks? And of course, there's also a question. I mean, is it really true that Wi-Fi is not sufficient? And I think when you talk to some of these operators, it does seem to be the case that actually Wi-Fi has a lot of problems, too much congestion, et cetera, et cetera. So there does seem to be at least interest on the part of some of these operators to start thinking about deploying cellular networks in these environments. But then the question is, well, what are really the networking requirements for industrial wireless? So it really depends on what we want to do. There's no one application, and the different applications would really drive what we need the wireless network to do. So what I want to talk about here is various Bell Labs robot drone projects that have a networking component. Not all of them are stuff I'm working on. Some of them are done by Sarah and Hui and others. They kindly gave me permission to mention some of what they're doing. And also talk a little bit about the network requirements arising from each. And going back to my earlier disclaimer, it's mostly engineering for now, sort of trying to get these systems up and running and working. But for those of you who are interested in the more theoretical side of networking, I think there's a lot of untapped opportunity here for actually generating models around some of these networks. I mean, the applications are different. And also there's maybe some flexibility in what the application does that we don't have in other networking problems. And actually tying into the reading group talk from this morning, I mean, clearly there's very tight latency requirements for some of these applications and the way you can apply network calculus type of things. So I think generating the models for these, there's some interesting work could be done here. So I'm going to mention 4 projects here. Probably only get time to talk about 3 of them. I titled the talk "Talking to Robots and Drones." That was partly taken. I saw there was this book, "Talking to Robots." Maybe it's a little bit different because that's really about humans actually interacting with robots. But I thought it was a nice title because, in some sense, a lot of what we want to do with networks in these environments is talk to these agents. So we want to provide the ability for some controller to talk to a robot, to talk to a drone. So the 4 pieces of work I want to talk about, this one is not mine. It's Hui and Sarah and our colleague Ilya in New Jersey. That really tries together, okay, what are the robotics requirements with the networking requirements? As you change the network performance, what actually happens to robotics? So that's one project. Second is piece of work we've been doing, trying to look at, okay, how well can you teach a robot to do things? an environment. In particular, how well can you teach a robot to avoid obstacles? And then what are the networking requirements if you want to actually run that solution? So I'll talk about that a little bit. The third project, again, is not mine. It's Sarah. Lou, is Lou here? Yeah, Lou's here. And again, I'll call you Ilya. I'm not going to really talk about that today, but I think that would be a good, that'd be another nice talk to have at some point. There's a really nice body of work here. So I'll let somebody invite Lou and Sarah to give that talk at some point. And then ground robots are fun. Flying robots are even more fun. So I just want to talk about a little bit about a project we have, which is really trying to monitor industrial facilities via drones. And again, talk a little bit about what are the networking requirements if we do this. So this is a drone flying in an indoor farm. So I wanted to mention a little bit of what we're doing there. Okay, so before we actually get into any of the work, a very quick primer on robotics in terms of defining what we actually need the network to do if we're going to run a robot in a factory or a warehouse. So all our robots, both the ground ones and the flying ones, run the ROS, the so-called robot operating system. So apologies for those of you who know ROS. I'm just going to spend a couple of slides defining the main features of ROS. ROS is notoriously very complicated. You can have whole semester classes on ROS that even don't cover all the features. It has many different aspects to it, but this is just going to be the 2 or 3 slide introduction. So basically, from a networking point of view, ROS is a peer-to-peer network. So you have a set of objects in the devices in the network that are controlled by ROS nodes. A ROS node could be anything that's useful in a robot network. So it could be a sensor, it could be a controller on a robot, those type of things. And then they communicate by what are called topics. So we have ROS nodes and we have ROS topics. A ROS topic is it's just a communication, a method of communication. And essentially, the communication is a publish-subscribe system. So any node can define a ROS topic, which you can then publish information to. And then other ROS nodes can then subscribe to that ROS topic and get that information. And then you have something called the ROS master, which basically controls that. It will allow nodes to advertise topics, and it will allow nodes to figure out which addresses to subscribe to if they want to hear the information from a robot. So this is not meant to be legible, but this is just showing our ground robots. This is the ROS network. So the ovals here, these are the ROS nodes. These are different components, both sensors and controllers in the network. And then the rectangles are the ROS topics. And these arrows are showing, like, this oval is advertising this particular topic, and it's subscribed to by this node. And just something a little more legible, blowing it up a little bit. You can just see there's quite a lot of complexity here in the network. So this is move-based. This is a very fundamental component that actually does a lot of the navigation on the robot. So it will subscribe to a bunch of topics, and it will also publish on a bunch of topics. So first of all, it's just to show that these networks actually get quite complicated. That when you've got all the different controllers, all the different sensors in the network, there's a lot of communication going on. So you do need a good network. And also, again, as I said earlier, if the network quality is not good, then bad things can happen. So again, what exactly is the network doing here? Well, the other major component that we need to think about when we think about the network is, well, what actually is communicating over the air? And the way we design most of our networks is to try and pull as much of the intelligence off the robot as possible into an edge cloud system that's sitting in the facility, and where you try and keep most of the intelligence. And the reason you want to do that is it makes the actual devices cheaper. It means you actually can have a lot less processing on the device, and especially for the robots that fly, it saves you a lot in terms of battery life. So in general, and I won't go through all the details of this, but to a first approximation, anything that you can pull off the drone, we want to do that. So in the cloud, we'll be running all the nodes and everything for localization and navigation, and it will only be the very low level functionality for the actual sensing and actuation that you actually want to have on the robot itself. And then, but obviously, what the robot sees and has to be communicated up to the cloud, and then what's all the decisions here have to be transmitted to the robot itself. So there's a lot of communication going across the network. So the network is really gluing together what's on the cloud side with what's on the robot side. And again, I don't want to go into the exact details of this, but fundamentally, you want to pull as much off the robot as possible and put it into the cloud. Again, just a very quick primer in terms of how you do navigation. So obviously one of the fundamental things you want to do with a robot is actually make it move and go where you want it to go. And there's really two algorithms that essentially when you're sending the robot, and this is both for the flying ones and the ground robots, that will really control where the robot goes. So first of all, if say a robot is here and you want it to send a destination, first of all, you'll have some map of the facility, and based on that, you will calculate a path from the source to the destination using your favorite routing algorithm, A-star, whatever. So in this particular case, the path goes from here round there. And so the global planner is basically computes a path from the start to the goal based on some static representation of the environment. But of course, as we saw in the factory environment, there are people walking all over the place. So you can't necessarily just follow the path, because there may be things that are not on the map. So then you have a local planner whose job is to adhere to the global path whilst using sensors, for instance, LiDAR, to avoid the local obstacles. So that's the first thing. So that's fundamentally how we do the navigation. And then secondly, the algorithms that actually do the navigation, they are using what's called a cost map, which is fundamentally, it's basically a grid that says, okay, what are the parts of the network that the robot, the environment that the robot can go on, and which parts does it have to avoid? So you can really see it here with the colors. So the darker colors are places that the robot has to avoid, both the fixed walls and also this temporary obstacle. You can see it here as dark green. And then as the colors get lighter as we go into more space. So this is essentially a representation of where the robot can go. So the local planner that has to decide how we get around the obstacles, that has to that uses this cost map representation, which comes from the sensors, to basically say, okay, what's the local environment? How do I get past the obstacles? And just to say where we do this work, so in our facility at Murray Hill, which is very, 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 very empty. It's fortunate we have a lot of space, and so we have a robot playground where we experiment with these things. But we also have a factory in India where we actually deploy these algorithms. And similarly, we have a drone playground, and we also have companies that we're working with who are actually trying to deploy the drones. So that's kind of the primer. So now I'm just going to talk about some of these projects that we're currently working on. So the first one is the one that's adaptive robot edge communication over wireless. This is the one that, in some sense, has the closest tie-in between the networking piece and the robotics piece. And this was a project where we were really looking around to try and figure out, has anyone really looked at sort of doing network measurement over a robot network? So robotics people tend to not spend a lot of time thinking about the network, and networking people tend, on the whole, not to spend a lot of time thinking about robots. So as far as we could tell, there wasn't a whole lot of work sort of measuring traffic over a network. So Sarah and I thought this was a hole. So we had Hui last summer to come and help us think about this problem. So what were the conclusions of this work? So first of all, what were the questions? So the questions were, how does the robot operating system react to bad network conditions? If the networking gets bad, what will happen? So we're familiar with, say, if you're on your phone, what will happen if the network goes bad, but what will a robot do if the network goes bad? So that's question number one. Secondly, can we actually improve it from a networking perspective? Can we change what goes into the network to make it react better to bad network conditions? And then lastly, from a robot perspective, can we actually drive the robot differently to make it react better to poor network conditions? First of all, just an experiment to just show in general what will happen if the network is bad. So this is the robot that Sarah Nui have. It's a clear-path robot, and they've been driving it around the Nokia company building at the Nose campus, soon to be departed Nose campus. And they started in this area here, and the colors represent the network conditions. So these are the signal strength, the RSSI values as we go from the start to the end point. And as you can see, as we get away from the start point, they're getting away from the access point, the network conditions are getting worse. So what does that do in terms of the network quality? So what we see here is we see the robot. Maybe I'll just pause it 1 second. What we see here is the robot driving along. So this was the area where the network conditions get worse. The robot is driving along, and you also have a first-person view. So you have a video showing where the robot is going, and as it's going along, the network conditions get worse and worse. Whoops, didn't mean to do that. So the robot's driving along, and as the network conditions get worse and worse, first thing you see is that the video is starting to break up. This is maybe not so important. You want to have some idea of where the robot is going. So as the network gets worse and worse, the video starts breaking up. Maybe more seriously, as the network condition gets very bad, all of a sudden the actual protocols that are running the robot stop working, and the robot here. So the video has died, and now the robot has died. So something's gone wrong on the network. So the fact we have a poor, the only thing that changed was that the wireless network got worse. So why did that happen? So first of all, this is just to show as we go further distance, so the RSSI went down. We showed it with the colored points before, and we can also see the capacity of the network went down. And basically, as the network capacity went down, we saw the robot stop. And the reason this happens is for a couple of reasons. So it's illustrated by this plot here. So first of all, this is showing all the traffic that's going over the different topics. So remember that we have this whole publish subscribe network where the different components are publishing and subscribing to different ROS topics. And we're showing here the capacity on all the different topics as the network condition is good. And then this is just a representation of what happens when the network conditions get very bad. So this is actually a different experiment, but it's showing roughly what will happen to the traffic over ROS topics as you affect the network capacity. So what we can see here is that the traffic on different ROS topics is very different. So these two top ones here are related to LiDAR and general positioning information. So these are obviously the ones that consume the most traffic. But as you can see, and also there's both a mixture of TCP and UDP. So obviously that has effects in terms of the buffering and the retransmissions, etc. But as the network gets very bad, you can see that the ordering of the topics actually is not maintained. So we have these topics that are consuming a lot of network bandwidth, but when the network gets bad, those basically drop to near zero in terms of performance. And obviously LiDAR is very important. If you want to know what your scenario, what your surroundings are, you need to know, you need the LiDAR to get through. And this is really showing what's happening. If we look at a lot of these topics, so again, these are general topics related to the LiDAR and the general positioning. If we look at the network backlog on all of these topics, as the network conditions get bad, we can see that basically there's just the queue backlog just blows up. So there's really no reaction of the robot network to the poor network conditions. So it needs a certain amount of bandwidth. It's throwing all this data into the network. The network gets bad. It's still throwing all this data into the network, and it just backs up, and the service curve gets gets worse, and so we get a high delay, and things are not good. So obviously you want to prevent these type of things. So one goal would be, I mean, the network didn't go to zero, so the question would be, can you actually do things to make things better? So Sarah and Hui did look around for a lot of the literature in terms of networking and robotics, and there wasn't exactly zero literature, but there was not a huge amount. And I won't go through all these references. Maybe the one I will talk about, because this seems to be the main paper that shows up when people talk about networking and robotics, is this one, Pound, a multi-master ROS node for reducing delay and jittering wireless network. So it's basically a way to reconfigure the publish-subscribe network, the peer-to-peer network, in order to make it work better with the type of traffic you get over wireless networks. So it makes the delay and jitter better, but it's still not reactive. It's basically just trying to make the network better, but it really doesn't, if the network is fundamentally bad, it really doesn't say anything about how you would adapt to that behavior. So what Sarah and Hui were looking at was really, can we actually, if fundamentally things go wrong, is there a way to react more gracefully? And they came up with a nice protocol, adaptive robot edge communication, basically trying to make the platform, the robotics aspect sort of network aware, so you can get control degradation when things go wrong. So without spending too much time on the setup, this is going to be simulation because we want bad things to happen, and generally you don't want to make bad things happen in a real deployment because people might not like it. But essentially what we did was we had a simulated world where we're running robots in a simulated world, and as mentioned before, it's a cloud robot system where what's happening on the robot needs to talk to controllers in the cloud, but we're going to run this to a network simulation, which we will feed with real network traffic traces. So we can feed into a network simulation real world traffic patterns, and we want to see if we can figure out how to make the performance work better. And in particular, we're going to focus on one particular topic, which is the LiDAR topic, which transmits the LiDAR information from the robot to the controller. So most people know what LiDAR is. It's a sensor that will essentially tell you as you go in at 360 degrees around the point, it will basically measure the distance to the obstacle. So you can imagine this scan happening that basically is telling you, I'm a robot, what's in my vicinity, and one control you have, so one very simple control you have is the frequency of the LiDAR. So what this shows here is for a real ROS deployment, what's the bandwidth on various topics as we decrease the bandwidth, the LiDAR frequency from 10 hertz to 1 hertz. So some of these topics are not related to LiDAR, others are, but as we go from 10 hertz to 1 hertz, we'll see the amount of traffic on that needs to be transmitted goes from this high value to this lower value. In particular, it goes from about 1.5 megabits to 600 kilobits. So then one question you can ask is, okay, so let's suppose that we reduce the network availability to 700 kilobits. So that's basically in between what's required for 1 hertz LiDAR and a 10 hertz LiDAR. So going back to the earlier experiment where you run a robot with different network conditions, can you see, okay, if you change the application so it's actually sending LiDAR less frequently, will that affect the robot behavior? And the answer is yes. So I think I can run these two videos simultaneously. Yeah, there we go. So on the left here, we're running the LiDAR at 1 hertz. And basically what we're going to see is the robot keeps moving as we get to a place where the network conditions are bad. So the robots are going to run, we're going to get to a place where the network conditions are bad. And if we're running LiDAR at 1 hertz, then the robot is going to keep going. But if we run the LiDAR at 10 hertz, we're going to get to this point where the network is good. As we saw before, it's just going to keep throwing it's just going to keep throwing data into the network, and then nothing gets through, and eventually the robot just decides to stop going. So this is the first experiment. Yes, by reducing the LiDAR frequency, you actually get better response to degraded network conditions. However, this comes at a cost. So suppose you have an obstacle in the way. So again, starting things up. So then this is just trying to understand what happens if you're running your LiDAR at 1 hertz and an unexpected obstacle shows up. So the robot is going here, and at some point the robot is going to, an obstacle is going to appear. And this is all simulating the full ROS stack. And we see that effectively it can't react to the obstacle soon enough. It basically just goes and sits right in front of the obstacle. Whereas what we saw here is that with the 10 hertz LiDAR, it goes around the obstacle. So we basically, these two very simple experiments on the previous slide and this one have shown two simple things. One, when the network gets bad, 1 hertz LiDAR is better than 10 hertz LiDAR, but still if we show up, but this may be not sufficient for some applications. If we have an obstacle in the way, we really need the higher frequency LiDAR. So there's an obvious solution to this. So is there a way we can get the best of both worlds? We still want the robot to get around the obstacle. And the hint, of course, is, what do you do if you can't see and you're driving? Or what do you see if, it's harder to see things going when you're driving? What do you do? You slow down. So then the next question is, so really this is the first piece. The network is degraded. We changed the network application, but now can we actually change the robot application? Can we actually do something different with the robot to react to the network condition? So this is, this is now saying, okay, before we were driving the robot at 0.5 meters per second, let's go down to 0.2 meters per second, and then see what happens with the same configuration. So we've now got the LiDAR at 1 hertz, so we've got that aspect, but we're now going to drive the robot more slowly. So I'm going to speed it up a little bit because the slow robot takes longer to get anywhere. So this is the situation where the LiDAR is coming slowly. It's only seeing the world slowly, but the obstacle comes, and it's in time to actually replan around and do also those sorts of things. So basically, the conclusion of this work is the vanilla ROS really does not try to adapt gracefully to poor network conditions. It just keeps dumping data into the network. Bad things happen. So obviously, prioritization of critical ROS topics will improve that performance. But beyond that, some ROS applications should be aware of the network conditions to try to generate less traffic when the network conditions are poor. But this may require changes to the robot behavior. So in terms of the sort of networking and theory implications of this, I think what doesn't exist at the moment is really a nice model that really tries to capture all these things together. So a model of the actual network in the facility, a model of how the robot applications are generating traffic to the network, and then the model of what the robots are actually trying to do. And I think there's actually scope for trying to generate better models for this to try and really understand, how does the delay feed into this? So ultimately, you have a general goal, right? The robot needs to get from A to B as fast as possible without anything bad happening. And so that's your ultimate utility function. But you've got many controls in terms of the network layer, the robot layer, to do all these type of things. And I'd also mention a number of people are also starting to look at, can you also change the routing? So all of this was done with no change to the routing. Some people are looking at, okay, if you have information about the RF quality in different parts of the facility, maybe you should even route in the places where the RF is better and you have better network conditions. So that's, question, absolutely.
Cannot we imagine a solution in which the robot can stop and take the time that is necessary because of the poor condition of the network to do the calculation of the new pass and then restart again?
Yeah, I mean, of course, in some sense, the going slowly is just a version of that. So, but then again, that's saying that you're doing something different with the robot. So, and I don't think this is anything, as far as we know, there isn't much of a literature in doing these sorts of things, specifically based on the network quality. That really, so that's in some sense what this work is doing. But there's other things. You could just stop and recalculate and then go on. But going slowly is another version of that. But yeah, so what's the right way to do? But understanding what happens in different versions of this.
are okay with the network.
Yeah.
You go slower when the population are.
Exactly, and you know you can also do it in terms of like how cluttered is the area. If in a very wide open space, you know there are not many people there, you can again do different things. Yeah.
When you said it continues to receive the
Yeah, so it's slowly, literally, as in it's going. The quality is low. Yeah. Then I think ultimately you can't do anything, at least in our current environment, right? Because it literally, most of the control is going on in the cloud. So if you can't talk to the cloud at all, you really have to stop. That's what you mean. Yeah, so I mean, as I say, literally at the moment, it literally can't do anything if the network is fully broken. It can't like back up or anything like that. There's really no intelligence that just lives only on the robot. But you could imagine things where you have, you know, some sort of like recovery mechanism that only lives on the robot and tries to, you know, go back to a, you know, there's many things you can do. So as I say, I think this is just at the early stages. I think there's a lot of stuff to be done. Yeah.
When it looks down, it may have an effect on other robots that are maybe waiting for that robot.
Right. So we actually have a lot of work on multi-robot coordination. So Sarah has a project on just the collision avoidance, but we also have I'm not going to talk about today, a whole sort of orchestration project, which is how do you really plan out the paths for multiple robots? And a very big part of that is, on the whole, you give a plan to a robot, which is like, where will it be at different points? And typically never goes at the speed that you gave it exactly, because then things that happen. So one of the things we've been looking at, you know, what are the conditions where you should pre-plan and those sorts of things. But exactly, yeah, if you do something unexpected for any reason, at some point other entities need to know about this. So that's a whole another set of things that some people are working on. Okay, problem number 2. So this is really how to bring reinforcement learning as a mechanism for collision avoidance, and how does it affect the network requirements. So the fundamental question here is, can we use reinforcement learning, because it's kind of paradigm everyone wants to use for every problem, to really look at the ROS local planner, the one that does the local path planning. How can we make it more responsive to unexpected obstacles? So this will be quite fast. Hopefully most people have seen the reinforcement learning paradigm. This is the picture that's in every reinforcement learning talk. So you have an environment and an agent that takes actions in the environment. And so the environment has a state, and when the agent takes an action, the state will change and you'll get some sort of reward. So the classic place where RL has been wildly successful is in games. So playing video games like Pong, the agent will move the paddle. The state is the state of the game. It could just be the image. So what deep RL, which is RL that uses neural networks, it's been able to sort of use a neural network to figure out what's the game state and then predict and then figure out what's the right action to take. And generally RL can do better than humans in many of these games. So how can we utilize RL in ROS? I mean, in some sense, this is a little bit of an ironic situation, because the very early RL algorithms actually came out of robotics. They came out of sort of maze exploration for a robot to figure out how to get to a target. But because fundamentally what you're doing on a robot is trying to take actions to perform some task, it seems like a nice application of RL. So what we're comparing against, so again, we're trying to do this for the local planner. This is the routing device that's trying to follow a path, and it gets round sort of unexpected obstacles, people in front of the robot. So what's the baseline here? The standard algorithm that goes in most ROS stacks is called DWA, the dynamic window approach to collision avoidance. I won't go into the details, but basically what it does, so the control on the robot is 2 velocities, the translational velocity and the rotational velocity. That means it will go in a circular arc at any given point in time. So what you do is you just take a set of feasible circular arcs that the robot is able to do, and you just compute a cost for each one, where the cost depends on how close will it adhere to the global path, and would it, that the circular arc hit anything. So this is the standard algorithm. It tends to be slow to respond to moving obstacles moving around, and actually it's got a bajillion parameters that require a lot of hand tuning. So because of this reason, RL algorithms just can learn what to do. It's starting to get attention as a framework for the local planner. So this was not original. There's a very nice thesis out of Hamburg for applying deep reinforcement learning to navigation of mobile robots. But in order to run reinforcement learning, you basically need to know what's your state space you're going to work in, what's your action space, and what's your reward function. Those are the three things you need to define if you're going to define an RL problem. So our state is going to be based on the cost map we talked about earlier. So first of all, the action space is going to be easy. The action is just the velocities you give the robot. You give it a translational velocity and a rotational velocity. But the state is going to be based on the cost map, which really comes from this array, which is a so-called occupancy grid, which basically says what does the robot see in its vicinity. And what it sees comes from both a static map it will have of the facility together with a LiDAR sensor. So what we do is we have the robot and it creates this occupancy grid which says in all the area around it, which are the areas I can't go to. And then you also have a notion of the global path. This is the path it's trying to follow. And typically we follow the Hamburg thesis and we discretize this path. We basically put lots of points on the path that we want to get to. And then we take this, which is in Cartesian coordinates, and we turn this into polar coordinates. So this picture is exactly the same as this picture, but it's in polar coordinates. The horizontal axis is the distance from the robot. The vertical axis is the angle. The red splodges are the obstacles, and this white square here is going to represent the waypoint. And now we've turned it into a problem that's a bit like a video game. So in some sense, we try to take the agents that work well for video games and apply them to this problem. So what we want to do at any given time, we want to get to the white square in this polar system whilst not hitting any of the red. And then what's our reward function? I won't go too much into this. It's kind of standard. You want to get a good reward for getting to the next waypoint. You want a negative reward for having collisions, etc., etc. And you also, generally these so-called sparse rewards, which are only happen at the end of a path, they tend to take longer to learn. So we also give so-called dense rewards. We give some reward for getting closer to the goal, and both in terms of distance, Euclidean distance, and also an angular distance. So if we're pointing towards the goal, that we get a better reward. But we want to do this without hitting anything. In terms of the RL algorithms we apply, I'm not going to go into the details because this could be a whole separate talk in terms of defining different RL algorithms. But for those of you who are a little bit familiar with RL algorithms, we basically try and use some of the latest papers, which did actually make quite a big difference in terms of earlier RL algorithms, where we use the so-called soft actor-critic algorithm with data augmentation. So just to define these terms, actor-critic algorithms, you have two neural networks. One neural network is trying to, for a given state, trying to define the action that you're going to take. And then you have a critic algorithm, which basically evaluates that, which basically says, was that a good action or not? And you train these two actor and critic networks separately. It's a soft actor-critic algorithm because instead of just trying to optimize some sort of long-term aggregate reward function, you also put in an entropy term to basically encourage exploration. You encourage sort of diversity of behavior. And then we also do data augmentation. So classic RL would you just run it in the environment and you just train it on the states that you see. With data augmentation, we use standard data augmentation or image processing algorithms where you do random shifts and random rotations of the data to try and make things a little bit more robust and have stability. And as a comparison, we compared against a so-called proximal policy optimization algorithm. It's a policy gradient algorithm. I won't go into the details, but it's one of the standard. If you take the stable baselines RL library, which is one of the standard RL Python libraries, it's one of the main ones. So just to sort of show how when you bring all these things together, how well it performs, most I'm just going to show that via a video. So the first thing we're going to show is how we do the training.
So we don't train with a real robot. We just simulate lots of these environments where we can do the training. So we have like a Cartesian space, and then at all times we convert the sort of Cartesian representation of the local space into this polar representation, which is what we're going to see on the real robot. So we're going to basically take a simulated environment where we can just very quickly give the RL agent many of these examples and try and get it to figure out its performance. So if we run from the beginning, we can see that the soft actor critic algorithm in this environment, it pretty much has perfect performance. It can always find its goal if we think of this as the next waypoint. But for the similar amount of training, the sort of state-of-the-art algorithm for the standard Python libraries did make a bunch of mistakes. So this was a collision, this was another collision, and sometimes there are timeouts. Yeah, this is a timeout. So generally putting on all the state-of-the-art RL stuff, the soft actor critic algorithm, the data augmentation, it did seem to make a difference. But of course, the proof of the pudding is in the eating. How well does it work when you actually then take the trained agent and you put it on a real robot? So just to go back a little bit, so this is a scenario where we'll define the global path. We need to follow the global path, but after that's defined, we go and put a dynamic obstacle in it. So first of all, it's just a cardboard cutout of a person, and just to show what happens with the RL agent. So again, we define the path that shows up in what the robot is sensing, and it reacts pretty quickly, and we'll just figure out its way around there. So it still was trying to go on the path, went right through the obstacle, but the RL agent found its way around it. Whereas the baseline algorithm, it didn't really, it was much less happy with if you actually put an obstacle on a particular path. One other thing we tried was just a pure shortest path algorithm. So this is basically with the local planner, is trying to get to a waypoint in this map. One thing you could just do is just do a shortest path algorithm. It's funny that if you look at a lot of the literature, you say that it says you can't run vanilla shortest path algorithms in this sort of robot environment where you need a decision every sort of 5 times a second, etc. But if you actually take latest vanilla Python implementations of Dijkstra's algorithm, actually they're so blindingly fast you can run it in these environments. So we tried that as well, and this did work in this context. It got into the interesting things where the shortest path was kind of ping-ponging between going left around the obstacle and right around the obstacle. But you could do it without learning. You could do it with vanilla shortest path. However, when we actually have a dynamic obstacle, so I walked towards it and stopped, the learning algorithm reacted very quickly, went backwards and went around, whereas the baseline algorithm, it basically couldn't figure out, it really wasn't able to respond to somebody walking towards me. So it stopped for a bit and then walked straight into me. And again, the shortest path algorithm, again, couldn't figure out, it went straight into me. Similar thing, but now walking across, the learning algorithm backs off. It can figure out what to do, whereas the baseline, it just went straight into me. And the shortest path algorithm, again, it can't deal with the fact that the problem space keeps on changing. However, there is a problem to doing this. The reactiveness comes from being very nervous, and really trying to respond to the obstacles very quickly. If you have something where it's just on the map, we're just going through a fixed environment, the baseline goes through very smoothly, whereas the RL algorithm, because it's constantly looking for obstacles, it tends to be a bit jerky. So the next part of this project is really trying to sort of marry the two algorithms and get the best of both worlds. Okay, so coming back to the networking requirements, what do you need to do to run this type from a networking point of view? Well, actually, the networking requirements are not that onerous. So ultimately, all we're trying to do is take the LiDAR scan on the robot and send it to the cloud part of the network where we're doing these decisions. So ultimately, what we've got here is a 720-point LiDAR scan of 8-bit integers. 720 points, because typically the LiDARs we use, they're actually, it's a 360-degree scan with 1 degree resolution, but it's in 2 planes. They actually have, it's in a plane, but it does it in 2 planes. So you get 720 points. If you're doing this 5 times a second, the throughput is not that great. It is not that high. It's just 28.8 kilobits. So shouldn't be hard to do. But you do need the round trip time. The round trip time to take the information from the robot into the cloud, do the inference, and get the response back again has to happen in less than 200 milliseconds. And this performance has to be available everywhere, or calamity will ensue. We've definitely had cases where we lost the network and then it just merrily goes on its way, and bad things have definitely happened. So this is really a case where the network is really a delay. So again, tying into this morning's talk, it's really about having very good delay performance and reliable delay performance, so you can get the good network performance. I'm not going to talk about the multi-robot coordination. This is very nice work, but it's not mine. This should be a talk by, oh, this is just Sarah. This should be a talk from Sarah at some point. So let me not steal her thunder. Let me just conclude with saying a little bit about how the problem change when you start flying the drones. And I think it's fair to say that at the moment we're not really playing too much at the moment with the navigation of the drone, or doing reactive navigation of the drone, or really adapting to network conditions. That's still, the drone's a lot more fragile, so there's fewer experiments can be done easily. I think this is all future work. But I just wanted to say a little bit about what are the applications we're doing with the drone, just give a taste of the reasons why people might want to fly drones in these sorts of environments. So the real question we're looking at here is, how can we fly a drone, collect images, and then apply machine learning to do something interesting with the images that are captured? And then what are the networking requirements for that? So we have this project called Autonomous Industrial Monitoring, where really we're trying to glue together a whole framework where we're flying the drone, we're taking images into an edge cloud, then applying a bunch of machine learning, and then at the end of the flight we basically say, what's the drone seen? I think let me just I think it's easier to explain just by going straight to the video. So one of the things that we're doing is trying to do inventory monitoring with drones. So this is an environment where you have a whole bunch of boxes with barcodes. So one of the things we do is we fly the drone, and as the drone is flying, we're constantly taking images of the barcodes, and then we want to run them through some software that can. This is actually third-party software, but it's applying neural networks to essentially both detect the barcode and then read it. So you can see here that we've got the red rectangle. When it sees the barcode, it will detect it and then read it. Another thing that somebody at lunch mentioned, digital twins. We're also, of course, because the whole world likes digital twins, we're trying to build these 3D models. And actually, when the drone has seen something in a barcode, we're then trying to put it into a model and create these 3D representations. And another aspect of the work is also using it to fly in an indoor farm. Farming company where they want to fly drones to actually monitor the grass. They have these plants that grow up in very fast growth cycles, 14 days, and they want to be able to fly the drone around, so they don't need to employ people to go and figure out what's happening. So again, these are the images that the drone is seeing. And it's going to stop in a second. Let me just pause it. So what do the farmers care about? So they care about things like what fraction of the tray is covered by plants at any given time, so that gives a sense of what's the quality of the growth. They also want to detect objects in the image. So in particular, they care a lot about how much of the back wall they can see, because that's a good proxy for how well is the plant growing and various other aspects. Okay, let me just show. What's instead of going on? And then once you have all that in place, this is just a video. Ultimately, what the drone would then be seeing, this is a growth cycle in one of these facilities. So again, in 14 days, they go from basically the putting of the trays into the tower to having, I forget if it's kale or arugula. It's they have these nice leafy vegetables, which are grown with a fraction of the amount of water that's required. Again, this is just talking again about barcodes. So let me just, I think I'm more or less out of time. So let me just talk about the networking requirements for this type of project. So this is very different from what we had from the machine learning, from the reinforcement learning for driving the drone, because the throughput requirements are much greater. So, but again, this is not actually flying the drone. It's just actually how do you process what the drone is seeing. So if we assume that each image size, probably you get about 300 kilobytes per image, again, a 5 hertz image rate, so take an image 5 times a second. So that gives you a throughput of around 12 megabits, which is actually quite hard to get in reliably with a typical Wi-Fi deployment of this type of facility is definitely not enough. A lot of the time it's due to sort of congestion on the Wi-Fi. There's various other things going on, and so this does seem to be a case where actually putting in a dedicated network with better resource allocation and stuff is useful. But of course, for this case, it's only for the processing up the fact. So actually, the latency requirements are not so strong. Some lag can be. But I think again, going back to the sort of theoretical aspects, there's an interplay here between the flight quality, sort of how stable the flight is, how close it is to what you want to see, with the network bandwidth. Because as the network bandwidth changes, typically the flight quality changes because the control loops for the drone get worse, and then that affects the image quality, and then that affects the analytics performance. So again, coming back to potential future work of generating models that relate all these things together, I think we're trying to come up with some models that really try to sort of capture all those things. So the general goal is you want to fly a drone and get good analytics performance, but there's a bunch of stuff that goes into that. And so trying to figure out, okay, what are all the interplay between these different aspects? I think it's quite interesting. So I think that really concludes what I want to talk about. Thank you very much.
Time for a few questions. Are there some questions in the room? Yeah.
Yes.
Going back to the beginning of the talk and to the end, you spoke about private cellular deployment for industrial sites. What is not really clear to me is, are we talking about a different radio access, and this is okay? But when I speak about a private cellular network deployment, I imagine a base station and a core network. And then the following question is, do I have many edges that need to talk to each other? Or just I have one cloud that runs all the drones and or the robots?
I think at the moment we're basically thinking a facility would have a set of servers that would be running the edge. I think the more interesting maybe aspect to your question is how do you actually deploy in terms of the access points? And actually that's certainly something, again, everyone likes the digital twin concept at the moment. People are trying to build RF digital twins of the facility. How accurately could you model the RF in a facility and then figure out where you actually need to put the access points for this type of thing? And again, it's probably easier to do it with cellular than Wi-Fi in terms of it will adapt better to all the obstacles that you'll get in this indoor environment and those types of things. But I think typically you just assume you have a closet somewhere with a couple of servers that are running this thing. But I think the real question is where do you put your access points?
Thank you.
Other question? No.
Yeah, maybe it's a stupid question, but the trustworthiness of these robots. Can you tell us something? Where is actually this trustworthiness is situated? Is it on the robot, in the edge, or in the cloud?
So the what of the robot?
The trustworthiness.
Trustworthiness,
Yeah.
so security and unhackability.
Yeah.
Actually, I don't know that much about the whole security aspects, but I know that one of the things we're actually trying to do. Let me go right back. The basic cloud picture. This picture. If you get to the very low level, there's all the sort of basic motor control. They know, like we control the robot in terms of just saying, okay, we want to go we want to go with this velocity and this rotational velocity. But at the very low level, this then has to be transmitted in instructions to different motors and those sorts of things. So I know, at least, I don't know if it's ubiquitous, but some robots, there's a whole set of Siemens protocols that do this sort of thing. And we actually wanted to extract those instructions. We were able to do it because it was encrypted. So I know that there's encryption at the very lowest level because they don't want people coming in and kind of taking over your robot. But a lot of what we're working at, the ROS level, that's just playing over the air. So I think if you actually, we're not worried so much about this at the moment that somebody would come in, but obviously there will be applications where you need to make sure that it's trustworthy and people can't come in and commandeer your drone and that sort of thing. But, I sort of feel in an indoor facility where it's controlled by a company, probably that's less interesting than, say, these drone highways people are talking about, like doing that, or of course military drones. It's obviously a really big deal. So I think it's a big topic, but personally, I don't know a huge amount about it.
Some question on the bridge? Maybe?
Yeah. Coming back to your last use case with the video feed, you said the drones have generally very little compute possibilities. But if they had some compute possibilities, and for example, your image inference started with feature extraction phases, doing a little bit of pre-compute underneath the drone would greatly reduce the bandwidth usage.
Right.
So has this sort of trade-off been looked at, or are you assuming that?
Have you worked with Fabio on this?
No, I have not. I've seen his presentation. And
Yeah, that was exactly Fabio's question. And interestingly, we were talking to a startup that was founded by a Princeton professor recently who started looking at all these analog compute devices for doing inference. So he has this chip which supposedly does very low power inference, and he can support all the standard neural network architectures. But this question was also raised. Maybe you don't want to do the entire inference; you want to do feature extraction. Personally, this sort of doing things in the middle, it's the sort of thing where you kind of wonder: is there going to be a use case that really fits into that? Or is it always going to be one extreme or the other? You should either do it all on the edge or all on the drone. But so I don't know, but I think it's an interesting question. But the other thing I learned about that recently is this drone I showed in the video is really ugly. We kind of like kludged it together. So for commercial use, we're trying to come up with a third party. We're trying to get some drones, get some third party companies to build us drones that are kind of packaged in a nicer way. Now, in general, we want to keep the computation very light, partly because of what's the compute power on the drone, but also the battery usage. So the number one thing here, even getting 20 minutes of flight out of these things when they're doing everything is tough. So, but some of these third-party companies are now coming with actually TensorFlow installed on your drone exactly for these type of things. Now, again, whether you really want to use that because of the battery usage, I don't know. But clearly people are thinking about this, and I think it'll be a while before we actually try and figure out, can we actually use the TensorFlow embedded in these devices? But it's there because people are thinking about it.
I'm curious if you mentioned that between the network, the wireless network, and the compute, which is heavier, which is more intensive?
That's the question everybody asks, and we have no idea. So that's a good that's a good experiment to do. Yeah.
Other questions?
I have to. Sorry. In these use cases that you looked at, did you have any case of network congestion due to multi-user? because I understand you can get congestion because you are one instance is requiring a lot.
Yeah.
What happens if you have many robots and do you need some kind of admission control that it's proper to this application so that is not
Yeah.
found?
Personally, I really pretty much do all my experiments with one robot or one drone, but Sarah does it with multiple. So I don't know. Did you ever see, obvious contention because you were running more robots or not really?
So in our case, the network was really good because we were running our experiments, but that is one of the questions that we and I and Ilya together are looking into as well. So once we figure out how to do this graceful degradation for a single robot, now that you have many, how do you do that fair share, right? That's like one the logical next question that's on our radar.
And also, I mean, part of the problem is we only have a limited number of robots, so you can't stress this on the physical environment. But Sarah, I know, is looking at scaling up, at least in simulations. So you could also you could also look at these things. But I think what's interesting, I mean, if you go back to the earlier plot with all the different topics, I think it's better to look below the granularity of fairness between the robots, because each robot has all these very different communication requirements for different functionality. So I think I would say it's better to look at each communication channel, the ROS topics, differently, separately as just a session that needs to be dealt with fairly. So.
Was there questions on the bridge? So thank you again.
Okay, thank you for the invitation.